So, okay, I think it's not a bad idea to start this again. Okay, we are on the second topics of today. Remember that I already mentioned the fact that when you have the concentrated load on your beams, actually it could be columns as well, you know, on your steel structure. The concentrated load could cause the local failure, the failure at the particular location that the load is applied. And the next thing is that the issue about the situation where we want to connect our steel structure to the concrete structure, being the beam sitting on the concrete or the column, you know, connected to the concrete abutment. Okay, so all right, when remember, if it's a beam web yielding and web crippling, we already talked about that. Okay, so now when we place our steel structure, we can have two more: the crushing of the concrete and the bending of the plate. And the concrete crushing, we need to prevent the concrete from crushing. So to prevent that, we will find the area of the plate. Okay. We need to find the area of the plate big enough so that the concrete has big enough area to handle the pressure and it will not crush. Okay. And once you know the area of the plate, that will help prevent your concrete underneath from crushing. You know the size of the plate. The next is to calculate the thickness of the plate so that your plate will not fail under bending if it's thick enough. Okay. Now let's go to concrete crushing. You know, it doesn't matter what the picture is. Say if you have this picture where you have the size of the plate sit on top of the concrete. Okay. Now we already mentioned that if your load or pressure or bearing pressure is here, your concrete will not fail at the surface. It will fail somewhere down below where the stress is distributed wider, deeper. But unlike the local web yielding, this distribution is based on the 1-on-1 ratio. Okay, so let's write something on the note. Okay, if I have the steel plate like this, I should use this square to my benefit. Let's say if this is my steel plate. Okay, now deep down, because we use the ratio of 1-to-1 distribution, so it's easier. So it will go out 45 degrees like this. Okay, because it's 1-on-1. Oops, what is this? Okay, so the area of the concrete that will actually undertake the pressure underneath the steel plate. Okay, would have to coincide with the, oh, I think we're gonna lose, yes. I sort of know right away because, you know, what I write on iPad doesn't show up on the computer screen. I know I'm gonna lose it. Okay, we are back in business. Okay, the red area must coincide with the blue area, which is the area of the steel plate. So the area of the steel plate is called A1, and the area of the concrete that will undertake the load from the steel plate is called A2, and it must coincide with A1. Now, coincide means that they should share the same centroid, So, we would have the issue with this. Let's say, for example, I'm going to give you a few cases so that you can see. Let's say if I have the plate like this, but somehow this plate is installed on the limited size of the concrete. Let's say like that. Now, because the area A2, by using the one-on-one distribution, that means the area would have to go 45 degree and must coincide with A1. So I will go out, and you see, that's where I hit the natural barrier of the concrete. I don't have any concrete anywhere outside this. And likewise here, let's say if I draw everything on ratio 45 degree, you see that becomes the area of the concrete that I can have to resist the load coming in from the steel plate. Now this is limited by the natural barrier of concrete. But let's say this picture gives you a nice situation where everything coincides. So let's say if the situation changed to something where I cannot place the steel plate on the location that, say dead center of the existing concrete structure. If I have a steel plate like this, but this time, let's say, the concrete is wider on this side. What do you think the area of the concrete A2 would be? Again, we go with the same distribution. So it's a 45 degree out here, 45 degree out there, 45 degree out here, and 45 degree out there. You see, on the right side, I can go farther than on the left because I don't hit any barrier until this point. But remember that the area of the concrete that undertakes the load must coincide with the area of the plate. So that means, this guy hits the barrier first. So that means the area of the concrete that can take the load should be limited to just this. And you see, in this case, the area anywhere beyond this is useless because we hit the boundary on the left, and because the distribution has to maintain the one-to-one ratio, which, it's rather conservative, but it's a model that they use and it works rather well. So that means your A2 here is pretty much the same as your A2 here, despite your plate sitting on bigger concrete. Okay, so let's say I give you one more. Let's say if I place the steel plate at the corner like this. Now, using the same thing, distribute evenly out to 45 degree like that. Now it hits a barrier. Right here, it also hits a barrier. So when you hit the barrier, that becomes, your sort of a limitation. You cannot go beyond this. You cannot go beyond that. And because A2 has to coincide with A1, and you go out 45 degree here and there. So there you go. That becomes your A2. This one. Okay. So Another case here. Let's say, what if I have a very large concrete and my steel plate is only this size. The question is, can my A2 go to infinity? Can I have my A2 go as far as I want? The answer is no. They have put the limitation on this. So no matter how big your concrete area is, you cannot have A2 beyond the limitation. And the limitation is 4. So A2, no matter how big the area is available to you, cannot be greater than 4A1. Okay, so you can use as much as you want as long as the area A2 does not exceed A1. Okay, so now let's go back to our PowerPoint. So that is the formula. A typical, they start from this. Okay, that is the strength of the material you use, right? And that is the area A1 of the plate. Multiply by this ratio, which in the end would give you the area of the concrete here that actually is going to fail by crushing mode. And A2 is the area of concrete, A1 is the area of the plate, and they say here that this term should not exceed 2, which means if you put the square root away, it is A2 could not be greater than 4A1. Okay, and I should use the word concentric, not coincide, but you know, it's pretty much the same meaning. So that is the concrete crushing. You need to find the area of the concrete that is big enough so that the concrete will not fail. But the model that we use is that the concrete will not fail right at the surface that the area is equal to A1. The failure will occur somewhere underneath. And we could use the distribution of 1 to 1 to find the area A2. But we have the limitation that A2 should not be greater than 4 times A1. So with this calculation, you will know how much the size of the plate you should have. Because when you know the size of the A1, you will know this, right? And if your concrete is not big enough, you just have to increase the size of the plate so that you will bring more concrete area into carrying the load. Okay, so the trick part is just to take care of the area underneath. All right, so that's concrete crushing. So now, after you know the size of the plate, you should be able to calculate the pressure, right? So let's say if the size of the plate is known, if plate size is known, we can pressure can be calculated. So basically, what do you want to call it? B and N, the size of the plate, and then you have the load P coming on top of this, right? So the pressure is going to be equal to the P over Bn. Okay, so now we know the pressure or I can say I can draw the 3D model with the thickness. So you know the pressure. All right. So when you know the pressure, this becomes a sort of the uniform load acting on your plate. So now the trick is to know what kind of a structural model we can use to design the plate. Okay. So let's go back to this. All right. So let's say if we have this uniform load, well, actually they call it FP. Okay. This FP comes from, you know, the total load, the P, or the R, the reaction. It's P. I meant to write down P, and it's P divided by Bn. Okay, so it becomes the load. So you can always model the plate because it has a free end, right? So that means I can sort of take one free body diagram out of this, and let's say there's a support somewhere, and this becomes a free end, and this part becomes the free body diagram that looks like that. Okay, with this pressure. Upward, it's called FP. This is this one, the entire one. Okay, not just P, the pressure. All right. So if you have the beam, you know, this is your model. Remember that the plate will have to be slightly bigger than the beam itself, right? So if this is your plate, it becomes a cantilever beam with the support right at the end of this. Okay. Okay. And this part, oops. And this part is this. See, this red beam is in fact this free body diagram. Okay. So you say if you know the size of your plate, let me write on this page. According to this picture, you know, be careful because this is going to be your beam, right? And then you have your plate underneath. So the plate will be slightly wider than the width of the flange itself. But the critical section that you can consider that this becomes a fixed support like this. Oops. Is the distance that is equal to K away from the center of the web. That is K, and this K is equal to the K that we talked about before in local web yielding. All right, and once you have that beam, you can calculate the FP from the model. Now you are going to design the beam by using the cantilever beam model like this. Okay, so the moment is going to be equal to FP multiplied by the length of your cantilever beam, that's N, it becomes a WL squared over 2, or W is equal to FP, L is N, it's over 2. And this one here indicates that we are now considering that this beam has the width equal to 1. You can design the entire plate, but it's, you know, it's the same. So might as well design it with, say, the width equal to 1. Okay. So now you have this moment, which is your requirement. That's WL squared over 2. And your capacity is plastic moment, or Fy multiplied by the plastic section modulus of your plate. And the plastic section modulus, if you can recall, it is Zx is Bd squared over 4. But we say, you know, we consider the width equal to 1. So these terms become d squared over 4, and d this time depth is the thickness of the plate. So the Zx becomes just the thickness of the plate square over 4. Okay, and with a little bit of rearrangement, you have the formula for the calculation of the thickness of the plate. And this comes from, you know, just let's say I'm running out of space. So let's say the moment is equal to Fp, and then if that's your n after the calculation, it's n squared over 2. Now this moment cannot be greater than your Mn. Let's say if it's ASD divided by this, right? Or if it's LIFD, it's this. And your Mn is, of course, Fy multiplied by the plastic section modulus of the plate with the width equal to 1. So that becomes Tp squared over 4. Now you do a little bit of, you know, manipulation. That's you will get the thickness from. Okay, so that's how we can obtain the thickness of the plate, and yeah, right after we obtain the size of the plate. Okay, so that's the issue of the beam. We have another issue, but it's the same thing, but this time it's a column base plate. So for the column base plate, you know, now instead of having a beam sit on the concrete, you have a column sit on concrete instead. And with the same business, you cannot connect the steel column on the concrete abutment right away. You need the plate, and you need the anchor bolt to adjust the level of the column so that, you know, it sits straight. And with the same business, you need the size of the column. You know, like I mentioned before, the size of the column must be slightly bigger than, I mean, the size of the plate must be slightly bigger than the size of the column, so that you have the workspace to weld the column to the plate. And then this plate, you know, installed before, the anchor installed before, you can just put the plate that is already attached to the column on in here, and then readjust the level by, you know, using the screw to turn, and you will have the installation of the column. And just like the previous case with the beam, the size of the base plate will help prevent the concrete crushing. So you know the load of the column, and you calculate the size of the plate big enough to prevent the concrete crushing. And once you know the size of the plate, you can obtain Fp, right? And then carry on to calculate the thickness of the plate based on the same bending model. But there's something that you need to know, okay? That is, the nature of the base plate for the column is slightly different, because the shape of the column is like an edge like this, right? So when you have the plate, the concern is what would be your n for the calculation of the moment, okay? Because as before, this is Fp is equal to I mean the stress FP, right? Sorry. Ooh. FP is equal to P divided by Bn. So when you know the pressure here, what would be the N? Now we have two dimensions, okay? We have the cantilever on both axes. So naturally, you would want to try to make these two distances, not so much different from each other, because let's say if you put one distance much bigger than the other, that would become the governing scenario for the thickness of your base plate, right? So it's not very, very, say, efficient. All right. So they have done something and realized that when you have the base plate and the size of the column, the shape of the column is an eye like this, this is the rigid zone, where you can say no plate bending will occur in this zone. So this becomes rigid. The zone that is considered not rigid is the remaining here. So we have two strips, this one and then that one. So let's consider the number one first. They said the rigid zone here, is 80% of the width of the flange. So this N here would come from, let's say, you have the width B, right? So it's B minus 80% of the width of the flange and then divided by 2. That gives you N. In the meantime, if you look at the strip number 2, from number 1. If you look at strip number 2, they say 95% of the depth is rigid. And so therefore, this distance M can be obtained from the size of the plate in this direction, that is N, minus 90% of the depth, and then divided by 2. Okay, so that is the strip number 2. So now you have two cases, and naturally, the bigger one will give you the thicker plate. Okay, so if possible, you should try to make these two sizes, pretty much the same as possible. But design is fun because it's an art in itself. So with this, you should know that try to make them, let's say, not so much different. Okay. Now, what happened last year was this. They say they take it to the heart, Okay, I'm just gonna make it the same. So then again, whenever you calculate, you just go ahead and use it. So after the calculation of this and this, they got the number. So they got the size of plate right away. So they have okay, I'm gonna use my plate 20.72 and then 22.43. Nobody is gonna cut that plate for you. So after the calculation, you try to make them not so much different, but it has to be practical as well. Not so much different and practical. Let's say if you have this, you might as well use the round number. Okay, I'm just going to use the plate, the size of 21 centimeter by 22.5 centimeters, so like that. Make it more practical, because let's say, are you going to measure that and cut the plate yourself? Nobody's going to do that. Okay, so make them practical and make them, you know, efficient. And sometimes when you have this size, it's also difficult to cut and install. So you might want to use like, okay, 225 by 225. If you do it like this, you know, during the installation, the workers, you don't have to be concerned with which direction they should turn the plate. By using the same the square size, you would help facilitate the construction to a great deal as well. Okay, so that said, we cover everything in terms of the concept. All right, and the concrete crushing is going to be just the same as in the beam, you know, and the plate bending is also the same. So, but you know, you need to use the one that governs. Use one that governs. Okay, so that's it. The local failure of the beam, and then the design of the base plate and the, you know, the concrete that supports steel. Is there any question? You know, again, this is rather quick, and we are going to begin to look at the example, but I want the clip to just end here, and then you have another clip that will be purely about the examples. So if nobody is gonna ask me anything, I'm gonna stop the share and I'm gonna stop the record.